Alrighty, good morning, lads and ladies. Welcome back to Calc 2. Today is a very exciting day for us because today is the day that we are going to introduce and define infinite series. And this is the reason the class has the reputation it does for being a little bit difficult, because the concepts here are quite beautiful, quite deep, and a little bit on the challenging side, in the sense that there's a lot of new notation, right? There's some new concepts, and the new concepts are not anything more challenging than the concepts involved in section 7.8, where we were doing type 1 improper integrals. But there is also a lot of new notation and some new definitions. So the class sort of begins to pile here, right? With 11.1, we had just a bunch of theorems on sequences. Here, we're going to slow that pace down a little bit. I am going to introduce at least one new theorem today. But we're going to sort of start transitioning from sequences to the next level up of objects, which are series. So let me go ahead and dive in and get started. Your exams are graded, and the feedback, I was able to get the iPad working again for you guys. So everything is in there, and you should be able to see the written feedback on your actual work. So if you want to see the comments I left you, look at your written work file. Occasionally, I will type a comment in the little box on the test itself, but for comments on your actual work, corrections, that sort of thing, see the written work. This is MAC, that's a bad pen. 2312, section number 004, which is Calc 2. And the date today is the 21st. What we're doing today is we're going to begin infinite series. And this is section number 11.2. For the record, when I say the word series, I always mean infinite series, right? Finite series are boring as hell. There's nothing interesting about a finite series. So anytime somebody says series, they always mean an infinite series. I want to kind of begin with a question, right? And see if we can sort of feel our way to the definitions and things like that by thinking about something that is, at a glance, quite reasonable. Is it possible to add up all the terms of a sequence AN? And let me go ahead and suppose that that sequence starts at 0. And that's our question, right? So we know that that sequence AN is an ordered list of numbers, right? That's what sequences are. And rather than listing them or trying to take their limit, what I'd like to do here is try to add them all up. So this would be something like A0 plus A1 plus A2 plus A3, and so on, forever and ever and ever, amen. Such an object, we might want to give it a name, so I don't have to write this whole thing each time. So let me call it S, capital S here, standing for the word series. Is this something we can do? That's the question. Let me see if I can make a little bit of time to talk about that with you, Fabrice, at the end. So I think I did see an email of yours, but I don't think I ever got the work that was missing for those. And then in extreme brief, without the work, I really can't can't do much because the rubric for those questions are all built around steps in the written work, but we can talk in more detail. So the challenge here, right? The challenge in adding all these things up is not in adding any two of them. I could add A0 to A1, right? These are just numbers, and I can add two numbers. I could take those two numbers and add A2, right? So now I've added these up, and then I can add this next guy, and now you've got A0 plus A1 plus A2. The challenge is that, and of course I could add A3 to that after doing that. The challenge here is that the operation plus is a binary operation. It takes two numbers in and spits another number out, right? You add numbers two at a time. Yes, after class would be good. So the challenge here is that we add numbers two at a time. And you might say, well, I can add numbers three at a time or four at a time. Yeah, but really what you're doing there is like adding the first two and then adding the next, or adding the first two, then adding those two, and then putting those together. It really is a binary operation. It really is something that we can only do two at a time. And then we can extend that to do, finitely many at a time. But here, because the sequence AN goes on and on forever, this big addition problem would go on and on forever. Here, if we add just two numbers at a time, we will die before we finish. Right? Because there's infinitely many things to add up. So going two at a time, like A0 plus A1. Okay, take that. That thing plus A3. Okay, take that. That thing plus A4. Okay, take that. If we do it that way, I will never finish the task because there's infinitely many numbers. I'll never finish, let's say, because there are infinitely many things to add. So the answer to the question here is going to be yes. But in order to come up with a way to do that, we need a workaround for this problem. And the problem is quite serious. It's hard to wrestle with infinity. I'm going to show you today the standard way of doing things. It involves something called a partial sum and then limits. And it's very similar to how we handled type 1 improper integrals. Remember, with type 1 improper integrals, what we did was integrate, instead of integrating from like 0 to infinity, all in one step, which we couldn't do, we integrated from 0 up to some finite number, t, or r, whatever variable you use. And then after getting a formula for that, you took the limit as t goes to infinity. We're going to do something very similar here. Before I get into the details, though, so let me answer the question and then introduce some notation. So answer yes by using a trick very similar to what we did in 7.8. Where we defined the integral from 0 to infinity of f of x dx as the limit as t goes to infinity of the integral from 0 to t of f of x dx. Right, that was a sneaky trick that allowed us to integrate from 0 to infinity by saying, okay, well, I'll integrate from 0 to t, solve that problem, and then take the limit as t goes to infinity. And this worked. The analogous trick for series, among other things, requires a notation similar to the integral notation, but for addition. So the integral symbol here is a stretched out letter S. I don't know if you guys know that, right? We always think of it as just the integral symbol, but it's actually a stretched out letter S, and it stands for the word sum, like S-U-M, as in to add up. You can think of an integral as adding up all the values of the function over the continuum, over all the real numbers between a and b. I know we're used to thinking of it as an area, but it's the same thing. So there is a notation for stuff like this that is quite similar, but it uses a different letter. And hopefully you've seen this before in Calculus 1. So first, we need some notation. We're gonna get sneaky. We need symbols to represent the objects we're playing with, otherwise we're gonna have a hard time writing down anything meaningful. This is called sigma summation notation. So, this is a Greek capital letter sigma. And basically what it says is take the thing next to me inside of the operator sigma and add it up. So this is a shorthand for long addition problems. Here's how it works. Sigma of some stuff in here, say an, where n runs from like 1 to 5, would mean we're going to take these things, the ANs, which have the variable n inside of them, and add them up as n goes from 1 to 5 over the integers. So in other words, this means a1 plus a2 plus a3 plus a4 plus a5. And thinking about the question we're trying to answer, right, you can see why this notation would be convenient, because, you know, this stands for the sum of the first 5 terms of the sequence. In general, sigma from n equals a to b of some stuff, where the stuff involves n, is what you get when you add up that stuff as n runs from n equals a to n equals b over the integers. All right, just n is always going to be a whole number here. The place you will see this in Calc 1, of course, is with Riemann sums. When you were first defining areas under curves or approximating them using rectangles, the Riemann sum was written using the capital sigma notation. And if you're lucky and you have a good pre-calculus class, you'll get at least some treatment of this stuff at the end of pre-calculus. But I know not everybody does. So First, just a tiny bit of practice with the notation. This is all very abstract. Let's see if we can compute a few little sums. And then I will take the problem we're trying to solve here, the infinite series, and kind of couch it in the notation of the sigma. So I could calculate sigma n from 1 to 4 of 1 over n, or sigma k from 0 to 5 of k squared, or sigma m from 2 to 6 of the cosine of m. Just some examples here. Whoop. You guys can't see the first sheet. So each one of these expressions is a shorthand for a big addition problem. And I just want to write them out. I want to make sure we're comfortable understanding what the sigma thing here means. So let's start with the first guy. How would I begin expanding that out? Does anybody want to help me with this? What is sigma n from 1 to 4 of 1 over n? How would I write that out long form? Yeah, exactly. So it means I'm going to take numbers of the form 1 over n and add them up. So take stuff of this form and add it up as n goes from 1 to 4. So this would be 1 over 1, plugging in n equals 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. So the sigma operator, this thing, tells me to put pluses between all these guys. And then the bounds here tell me to let this symbol or this expression go from 1 to 4. So 1 over 1, that's n equals 1, plus 1 over 2, that's n equals 2, plus 1 over 3, that's n equals 3, and plus 1 over 4. And yeah, we can simplify this if we want. I'm not sure off the top of my head. Let's start back. Let's start here. This is 3 halves. 3 halves plus 1/3. I'll write it out. So I'm not very good at arithmetic. 3 halves plus 1/3 plus 1/4. So if I needed a common denominator here, it would be 6. This would be 9/6 plus 2/6, which is 11/6. And I still have that 1/4. And then a common denominator here. Let's just use 24. So this would be 44/24 plus 6/24 would be 50 over 24. A little bigger than 2, right? But the important part here is the first part. And this is what I'm wanting to make sure you're comfortable with. Sigma k from 0 to 5 of k squared would be 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. I'm not even going to bother finding the sum here. I just want to make sure we're comfortable with what the operator is saying. All right, that would be 0 plus 1 plus 4 plus 9 plus 16 plus 25. The last guy would be the cosine of 2 plus the cosine of 3 plus the cosine of 4 plus the cosine of 5 plus the cosine of 6. And those are nasty numbers. I'm not even going to dream about trying to find that sum by hand. Again, the purpose of this example is just to get us comfortable with what the sigma operator does when you put something in here. So are there any questions about expanding something like this from here? Okay. Let's see if we can take something that is not in the sigma notation and turn it around and put it in the sigma notation. So here I'll say express in the sigma summation notation. And for A, I will write, how about just 1 plus 2 plus 3 plus 4 plus 5. For B, I'll write 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4. And for C, I will write about 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. So I want to take each of these expressions and write them in that like condensed form with the sigma operator. And let's start with the first guy. So this is going to be sigma of something where n runs from somewhere to somewhere else, right? These are the pieces we know for sure have to be there. I'm choosing to use the symbol n, but you could use k or m or whatever you wanted. Usually we use n. If you had to write the terms, these as like terms of a sequence where this is A1, where this is A2, where this is A3, where this is A4, and this is A5, what would AN be? So I've got two responses there, and I like both of them. If this was 1 plus 1 plus 1 plus 1 plus 1, then AN would always be 1. So let me start by writing it like this. I'll say this is sigma n from 1 to 5 of AN, right? A1 plus A2 plus A3 plus A4 plus A5. And then we need to specify what the ANs are. And the two answers I got there were AN is 1 or AN is n. The correct one here is AN is n, right? Because A1 is 1, A2 is 2, A3 is 3, A4 is 4. If AN was 1, then these would all just be 1s. So we would say this is sigma n from 1 to 5 of n itself. And if you were to start with this and expand it out using the logic that we used on the previous example, this would be 1 plus 2 plus 3 plus 4 plus 5, right? Because you plug in 1 for n, and then you add that to what you get when you plug in 2 for n, and you continue on like that. Now let's try the same thing with part B. So here again, I'll just say, okay, this is A1, this is A2, this is A3, this is A4. So we're going to be looking at a sum from n equals 1 to 4 of AN. And again, we have to figure out what the ANs are. So I've got a 2 to the 1 for A1, 2 to the 2 for A2, 2 to the 3 for A3, 2 to the 4 for A4. What would A5 have been? There was a next term there. What would that next term have been? Yeah, very good, 2 to the 5. So in general here, AN is 2 to the N. So the final answer for this one would be sigma n from 1 to 4 of 2 to the N. And like we said, if you were to begin with this and expand it out, that would start 2 to the 1, and then plus from the sigma, 2 to the 2, plus from the sigma, 2 to the 3, and you keep going until you get to 4. The last one down here is a little bit trickier. I'll start the same way. All right, this is A1, this is A2, this is A3, this is A4, and this is A5. But I think it'll be helpful to play a little game with the denominators before we jump straight into the sigma notation there. What do you notice about those denominators? What kind of numbers are they? Yeah, they're squares, right? This is 1 over 1 squared plus 1/4 is 1 over 2 squared plus 1/9 is 1 over 3 squared. 1/16 is 1 over 4 squared, and 1/25 is 1 over 5 squared. So I think from here saying, okay, A1 is 1 over 1 squared, A2 is 1 over 2 squared, A3 is 1 over 3 squared, A4 is 1 over 4 squared, and A5 is 1 over 5 squared. From here, I think it's much easier to see that this is the sum from n equals 1 to 5 of 1 over n squared. Right, in other words, the ANs here are 1 over n squared because the numerator is always 1 and the denominator is always the square of the index. So that's the notation. All right, any questions on these two little examples here? So keep both in front of that so we're not too far. Okay, then let's return to the main thing. Again, our goal is to reasonably define the object we called S was A0 plus A1 plus A2 plus A3, on and on and on forever. And if I write this in the sigma notation, just kind of doing the natural thing, like that last problem, this would be the sum of AN as n runs from 0 to 1, 2, 3, but keeps going forever and ever and ever up to infinity. And that's the notation for an infinite series. And this thing is called the infinite series, whose terms are the sequence AN. right? So this is distinct and separate from the sequence. This is not the sequence. But the things that are being added up here are the terms of the sequence AN. We still have to tackle that problem. The fact that there's infinitely many things to add up here is an issue, because if you try to add infinitely many things two at a time, like we did in the first example where we're simplifying, then you'll die before you finish because there's infinitely many of them. Even the world's fastest computer will never get the job done without a trick. And the trick is to copy what we did with improper integrals. Which was, i.e., we wrote the integral from 0 to infinity of f of x dx as the limit as t goes to infinity, integral 0 to t, f of x dx. So in our series here, sigma 0 to infinity an, the an is like f of x. And the sigma is like the integral, right? The sum from 0 to infinity here is like the integral from 0 to infinity here. So if we copy this, that gives us sigma and from 0 to infinity of an. I don't want to use the symbol t for the limit here because t is generally thought of as a real number. When you see t, you think of it as like a time. I want to use a symbol that suggests I'm only talking about like whole numbers, positive whole numbers. And n would be a good choice, but I'm already using n here, right? N is the index. So I don't want to use a lowercase n, although your textbook does, and it is a bad choice of notation. So what we do is we write this with limit capital N goes to infinity, sigma little n from 0 up to capital N, right? Same trick. I swap this thing for a variable, and then out front put the limit as that variable goes to infinity. And then the inside is the same, a sub little n. And this is it, guys. This is the big deal. This is how you define an infinite series. And now earlier I called the thing on the left S. So we could also have just written S equals limit capital N goes to infinity. But then I want a name for this thing. The version of S, right? Sum from n equals 0 to somewhere of an, the version of S, that instead of going to infinity just goes to capital N. And the normal notation for that is S sub capital N. And again, your textbook elects to use a lowercase n here, which I think is a very bad choice of notation. Where S sub n is the sum from 0 to capital N of an, which is called the capital Nth partial sum of the full series S. And these words, partial sum, are very important. So the full infinite series, we call that S. We define that as the limit as capital N goes to infinity of the series that stops at capital N. And so that's the version of S that only goes out to capital N. We call that S capital N. And the word or name for that object is the capital N partial sum, right? Because it's a part of that series. It's not the whole series. It's not the whole sum. It's a partial version of it. This one goes on forever. This one stops at the capital Nth term. And the good news is that just like here, I can't compute the whole integral at once. No Riemann-Sum's problems, right? Problems computing the whole integral at once. But if you make the integral stop at some point, then I can compute that. Well, the same thing is true here. I can't add up infinitely many numbers all at once. I run out of time. But I can add up finitely many numbers, right? I do it 2 at a time if I must, but I can always add up finitely many numbers. And while you or me or a human being might get quite tired if n is a large number, if you can find a formula for this in terms of capital N, like here we used the fundamental theorem of calculus to find a formula for this in terms of the variable t. If you can find a formula for this in terms of variable n, then you can take that formula and send n to infinity. So this is how you define an infinite series. Before I get into any further definitions or theorems, I think it's wise to just look at some examples. So I'm going to write down some series. We're going to compute some partial sums. A word of warning. I don't have a red pen handy, so I'll use purple here. Just warning. Sn is not the same as an. And no matter what symbol you use down here, big N, little n, T, Q, R, potato, S potato is not the same as A potato. The S's and the A's are very different. Right? Sn is the sum out to the nth term. And this is kind of like the formula for the factorial in that it looks a little bit weird when you plug in small numbers for n. So I just want to take a quick peek at this. S0 would be A0. S1 would be A0 plus A1. S2 would be A0 plus A1 plus A2. S3 would be A0 plus A1 plus A2 plus A3. Right, that's the idea. The S's come from the A's, but they're not the same as the A's. And there are problems in your homework set. There will be problems on the test that are designed specifically to check whether you understand the difference between the terms of the series an and the nth partial sum of the series Sn. So questions on the notation or the definition? All right, let's get our hands dirty. I'm going to change it up here. I'm going to write the series as starting at 1. That's fine. Series can start wherever they want, right? Just like sequences, sometimes they start at 1, sometimes they start at 0. Often, I think it's more convenient to start at 0, but you can start them at 5 if you want. This guy starts at 1. So the first partial sum I could talk about here maybe even before that, if I write this series out, this is like 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus going on and on like that forever, right? That's what that guy means. And now my task again is to find the first 5 partial sums. Since the series starts at 1, the first partial sum would be S1. And this is just the sum from n equals 1 to 1. This would just be 1/2 to the 1, which is, on a good day, 1/2. S2 is not 1/2 to the 2. I'll repeat that. S2 is not 1/2 to the 2. It's 1/2 to the 1 plus 1/2 to the 2. It is the series stopping at the second term, or the n equals 2 term. So it's the first 2 parts of the series, or the partial sum associated with n equals 2. And that is a 1/2 plus 1/4. And what do you get here? Let's see, this is 2/4 plus 1/4. That's 3/4. S3 is not 1/2 cubed. It's 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3. So what's that? It's 1/2 plus 1/4 plus 1/8. And if you have a common denominator there, that's 7/8. You will probably see my arithmetic be weak a little bit today because there's a lot of it here. Just go slow and you'll be okay. S4 would be 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4. And what you might notice is that, compare S3 and S4. The first 3 terms here are the first 3 terms here. I know that that adds up to 7/8. I just did that. Right? This is 1/2 plus 1/4 plus 1/8 plus 1/16. And I know that 1/2 plus 1/4 plus 1/8 is 7/8. This is 7/8 plus 1/16, which is 14/16 plus 1/16 is 15/16. Yeah. Is that right? Yeah. And we wanted the first 5, so I'll do one more. S5 would be 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4 plus 1/2 to the 5. And this time I'm going to use that observation we just made. Like the first 4 terms here are the thing that I just computed. I know that the first 4 terms here is 15/16. So this is 15/16 plus just this last term, and 1/2 to the 5 is 1/32. Multiply by 2/2 here, and this will be 32, so that's 30 plus 1 is 31 30-seconds. All right, there it is. There are the first 5 partial sums for this series. Questions on this computation? Everybody Gucci? Okay. Down the road, I'm gonna find you a formula for Sn for this particular series. We'll actually be able to do that. I'll find you a nice formula for Sn, and I'll be able to tell you the value of this series using that definition that we had on the board just a second ago. But before I do that, I want to do one more little practice with just computing partial sums, and then we'll look at both of them as the full infinite series. So again, compute the first 5 partial sums for the infinite series here. This time we'll use S equals sigma. We'll go from 0 to infinity, just -1 to the n. So the ANs here are just -1 to the n, but the SNs will be something else. Since this series starts at 0, the earliest partial sum I could write down would be S0. And S0 is just going to be -1 to the 0, which is 1. The next guy, S1, would be the sum out to n equals 1. So that's -1 to the 0 plus -1 to the 1. So that's 1 plus -1, which is 0. I'll write it. 1 plus -1, which is 0. S2 is -1 to the 0 plus -1 to the 1 plus -1 to the 2. You see what we're doing, right? The S's compute the sum, but not the whole sum, just part of it, hence the name partial sum. So this is 1 minus 1 plus 1, and that's 0 plus 1, which is 1. S3 would be -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3. And I can take advantage of the thing we observed last time, that to go from S2 to S3, we're really just adding this one more term here. So I know that the first terms, 0, 1, and 2 terms here, these add up to 1. And then this guy is going to be -1. Maybe I'll write it 1 minus 1 plus 1 minus 1. But we really don't have to. We know that this should be 0. It's this guy, first guy is here, plus -1, right? Because -1 cubed is -1. One more. That's 4 is -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3 plus -1 to the 4. And again, that's going to be 1 minus 1 plus 1 minus 1 minus 1 plus 1 minus 1 plus 1. So that's 0 plus 1, which is 1. Oh, yes. So the question came in there as a DM, and it was, this is going to get more complicated eventually, right? Yes. Oh, God, yes. I'm just trying to be very gentle at the start. The game we're playing right now, finding the partial sums, is generally not the game through most of chapter 11. You remember in 7.8, most of the improper integrals we worked, you actually like solved the integral. You had to write it as a limit and then solve the integral and then take the limit. The analogous step here is finding a formula for the nth partial sum, right? Like solving the integral, finding the antiderivative, plugging in 0 to t, is like here, finding a formula for Sn. And if you thought finding antiderivatives was hard, finding partial sums is way fucking harder. Like finding a formula for the nth partial sum is in general incredibly hard. So we're going to be doing a lot of stuff like that comparison theorem, right? Where you built up an inequality and then you said, oh, okay, yeah, this integral converges because it's smaller than another convergent integral. Most of what we're going to do in sections 11.2 through 11.11 will be thinking like that. So I'm trying to warm you gently to this, what's going to be a very abstract set of arguments. But yeah, okay, here. So just finding the first few partial sums. Finding the first few partial sums, it's not hard, right? You got to write the thing out, you do the arithmetic. These two partial sums behave very differently, though. Very differently, right? This first guy, we had 1/2, 3/4, 7/8, 5, 15 16ths, 31 32nds. These are getting bigger and bigger. And the numerator is 1 smaller than the denominator. So these partial sums are getting closer and closer to something. As we add more and more and more terms to the series, the partial sums are getting closer and closer and closer to some specific number. I'll talk about that in a minute. Here, these partial sums are just going 1, 0, 1, 0, 1. The next one would be 0, then 1, then 0. And that difference in behavior exemplifies what we mean by convergence for an infinite series. So what I'm going to do now is define what it means for an infinite series to converge. And then we're going to return to those and other examples to discuss their convergence. So here we go. This is one of those big moments in class. The infinite series S equals sigma n from, all right, from 0 to infinity, but it could be from wherever to infinity, is called convergent if the limit defining it and this thing, remember, is the limit. We could call it just limit n to infinity of S of capital N exists and it's finite. Okay. So we say the full infinite series is convergent if the limit of the partial sums exists and is finite. In other words, the series is convergent, sigma an is convergent, if the sequence of partial sums is a convergent sequence. We say, so if this limit either does not exist or is not finite. Right, that is comes out to like infinity or negative infinity. Then we say the series S equals sigma n from 0 or wherever to infinity of an diverges. Put this somewhere special in your notes. This is a big deal, and we will lean on this for the next 9 sections in the textbook. It's the longest single conceptual run in the entire calculus sequence. Nowhere in Calc 1, 2, or 3 do you rely on a single definition more consistently through 9 sections than this. The only thing that comes close is the definition of the derivative, but you very quickly move away from that in Calc 1. So put this somewhere special. Take a second. Questions on the definition? Okay. Then just a bit of vocabulary. Let's say note. If the series S equals sigma n from 0 or wherever to infinity of an converges, then we call the value of this limit the sum of the series. Right? It's what you get when you actually add up all the terms. So remember, this thing is equal to this thing. Look back at the blue box definition from the previous page. The full infinite series is defined to be the limit of this guy. Right. Right, so we've got our definitions. Let's see if we can determine whether that first series we're applying S equals sigma n from 1 to infinity, and we have to converges or diverges. If S converges, find so our definition is right staring us above here, right? The infinite series is the limit of the nth partial sum. This guy is Sn. You can add that here if you wanted, right? This is I try not to mix the notations because I know it's a lot of writing. This is Fn. So let me just copy down what we wrote before. We previously calculated for this series and partial sum. Previously calculated some partial sums for this series. We calculated that S1 was 1/10, S2 was 3/4, S3 was 7/8, S4 was 15/16. And I'll just stop here for the purposes of this problem. In order to say whether the series converges or diverges, and certainly in order to find its sum, from where we are right now, what we need is to take the limit of the partial sums, not the limit of the ANs, not the limit of these, the limit of these. Right? And one of the first crucial things you must do is divorce in your head the idea of the AN and the SN. They're not the same thing, right? Remember when we did the computation, the SNs, what we got by adding up the first few ANs. S2 was not 1/2 squared, it was 1/2 to the 1 plus 1/2 squared, and so on. So what I would really like here is a formula for Sn, because then I can just take the limit. So what I'd like to do is to make some observations about these partial sums and use those observations to find a formula for Sn. It's kind of a what comes next problem, right? And I'll begin by asking, what do you notice about the denominators? Yeah, the denominator gets multiplied by 2 every time we go up 1, right? Which means that they're all powers of 2. So this first denominator, I'm just going to write as 2 to the 1. The second denominator, I'll write as 2 to the 2. 4 is 2 to the 2. Third denominator, 8, that's 2 to the 3. And this fourth denominator, that's 2 to the 4. So the denominator of S4 is 2 to the 4. The denominator of S3 is 2 to the 3. The denominator of S2 is 2 to the 2. The denominator of S1 is 2 to the 1. I would guess then that the denominator of Sn is probably going to be 2 to the n. But before I go writing anything like that, I need to address the numerators. What do you notice about the numerator as it relates to the denominator? Promise not a trick question. The relationship between 1 and 2, between 3 and 4, between 7 and 8, between 15 and 16. Yeah, it's 1 less. I swear, I'm not trying to trick you. So the numerator is always 1 less than the denominator. The denominator is always a power of 2. So I can write this as 2 to the 1 minus 1. 3 I can write as 2 to the 2 minus 1. 7 I can write as 2 to the 3 minus 1. All right, the minus 1 isn't in the power, obviously, it's outside. 15 is 2 to the 4, 16 minus 1. So this would appear to imply, starts to look like S sub n is a fraction where the bottom is 2 to the n, and the top is that thing minus 1. And we can check, does this match up with what we did before? Remember, we computed one extra of these guys before. I went out to S5 before. S5 was 31 over 32. If I plug in 5 here, what do I get? Well, I get 2 to the 5 minus 1, which is 32 minus 1, which is 31, divided by 2 to the 5, which is 32. So yeah, 31 over 32. This is good. So now, what can I say about the full infinite series S? Well, S is by definition the limit as capital N goes to infinity of S sub capital N. Which is the limit as capital N goes to infinity of 2 to the capital N, whoops, minus 1 divided by 2 to the capital N. And there are many ways to take this limit. You've been practicing with limits. The easiest way is to split it up. This is the limit as capital N goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. Two to the n over 2 to the n is 1. So this is limit capital N to infinity 1 minus 1 over 2 to the n. And as n gets bigger and bigger and bigger, 2 to the n gets bigger and bigger and bigger. So this is 1 minus 1 over infinity, which is 1 minus 0, which is 1. And we just worked out our first infinite series. Yay, we did it. What we've just shown is that the infinite series sigma n from 1 to infinity of 1/2 to the n comes out to 1. By calculating its nth partial sum, finding a nice formula for the nth partial sum, and believe me, this is in general a hard thing to do, and then taking the limit of that. Let's say finally, since the limit as n goes to infinity of the Sn exists and is finite, right? It was equal to 1, which is extant and finite. We learn that the series S equals sigma n from 1 to infinity of 1/2 to the n converges, and that its sum is 1. Another way to say this is that the series converges to 1. And there's a terrible joke that comes with this, and I apologize in advance, but I just cannot avoid the joke. An infinite number of mathematicians walk into a bar. The first one orders half of a beer. The second one orders a quarter of a beer. The third one orders an eighth of a beer. And the bartender says, "Fuck, I hate you guys," and just pours one beer. Apologies for the bad math humor. So quick, again, just a little note. In other words, we just proved that 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, going on and on and on forever, is equal to 1. That's what you just proved. Just proved that if you add up that infinitely many numbers, 1/2 plus 1/4 plus 1/8 plus 1/16, infinitely many numbers, you're going to get 1. And I never had to add infinitely many things anywhere in that process, right? And this is the magic of the little workaround that we found, the answer to that question at the start. This fact was known for a long time. The ancient Greeks, I don't believe, knew this. But if you look in like Ayurvedic math, like ancient Indian mathematics, they did know this. If you look at the origins of the word algebra, that's an Arabic word. If you look at ancient Arabic math during the just after the Muslim Revolution in what we call the Middle East now, they knew this, right? Didn't get to the Greeks, I don't think, for whatever reason. So yeah, good stuff, right? Let's look at the other one. Another S equals sigma n from 0 to infinity, -1 to the n converges or diverges. And I'll leave this one just like that. Okay. So I want to know whether this series, the other series that we played with and found partial sums for, converges or diverges. Again, we previously calculated S0 to be 1, S1 to be 0, S2 to be 1, S3 to be 0, and S4 to be +1. Finding a formula for the nth partial sum here is a little trickier than what we did with the last one, but I'll still do it for you. But you don't even need like a nice algebra formula for this. Remember, what we're trying to do is take the limit as capital N goes to infinity of Sn. What is that limit? So S equals then Sn. Yeah. So remember, this is what we need, right? The full infinite series is the limit as capital N goes to infinity of Sn. And I claim that you can tell me this limit even without a nice formula for Sn, just based on the first few things here. Because we've just learned that, maybe I'll write it like this. Sn is 1 if n is even, and 0 if n is odd. I'm trying to take the limit of that thing. Like if you want the graph of Sn here, that graph looks like this. 1, 0, 1, 0, 1, 0. And the next 1, 0, just goes on like that. So does this thing, Sn here, have a limit? All it does is bounce back and forth from 1 to 0. Is there a horizontal asymptote here that all these terms are getting closer and closer to? The next dot would be up here, and then the next dot would be back down there. Yeah, we want to be a little careful with our language here. So this limit is dne. The limit of the partial sums does not exist. All right, if you do want a formula for the nth partial sum, I can find that for you. It's going to be 1 plus -1 to the capital N over 2. You can check that this works. If you plug in an even number for capital N, this is 1 plus 1 over 2, which is 2 over 2, which is 1. If you plug in an odd number for capital N, it's 1 minus 1 over 2, which is 0 over 2, which is 0. So this formula does work if you wanted to just jump in with that. And then this piece is the piece that gives the dne. But yeah, this limit does not exist. Therefore, thus, the series S equals sigma n from 0 to infinity of -1 to the n diverges. So one of the things I need you to be exceptionally careful about as you work these problems is that you're using the language with great clarity. The word diverge and converge apply to both sequences and to series, as well as to improper intervals, but sequences and series. Here, if we say diverges, you could be talking about the sequence Sn, you could be talking about the sequence An of terms, or you could be talking about the whole series S. I'm looking for the answer regarding the whole series S. So please be very, very careful when you say diverges or converges. It's true, and it sucks that in the homework on WebAssign, if you click the one that says converges and the series is a convergent series, you'll get the right answer. If you click the one that says diverges and that series happens to be divergent, you will get the right answer, but that is nowhere near understanding what's going on. So you must make sure that you're writing out good full solutions, not just clicking until you get the check mark in WebAssign. That will be terribly destructive for the second exam. The solutions to problems in chapter 11 are paragraphs with words, right? At least full sentences. This limit does not exist, thus the series S equals sigma n from 0 to infinity -1 to the n diverges. Period. Make sure you're writing in full sentences. Make sure you're using correct grammar and syntax. And anywhere there is the possibility of something being ambiguous, like saying it converges, remove the ambiguity by being very specific. What converges? The series converges, right? What diverges? The series, S equals sigma n from 0, -1 to the n is what diverges. So we need to be exceptionally careful. Okay, that's about all I have for you today. Now I'm gonna do one more thing for you. I'm gonna give you a little definition, and I'll tell you what we're gonna talk about next time. Maybe I'll just kind of prime you for the discussion next time. Let's do it like that. You remember when we started section 11.1 last Monday, I asked you what kind of calculus operations could we hope to do with sequences? Because the sequences, the graphs are just dots. No hope for a tangent line, right? Although we did come up with a notion of derivatives by just kind of thinking of it as a continuous function. I said that there will be something like an integral, right? There is a thing like integrating sequences. That's what these are. So kind of our parting note and where we will begin next time is that a series sigma n from 0 to infinity an is very much the integral from 0 to infinity of the sequence an. Right, sequences are literally functions. They're just functions whose domain is the natural numbers. Well, a series is literally the integral of that function. It's just that kind of integral here has to mean something different than it does when you talk about functions of a continuous variable, because the graphs are so different, right? The graph of a sequence is just the dots. What do I mean when I say this? Well, I mean, if you look at the graph of your sequence, you suppose your sequence has limit L, although this isn't necessary for this analogy. And it could be anything, or maybe not even exist, and the analogy would still work fine. Then the graph of your sequence is going to look something like this, right? With terms getting closer and closer and closer to L. The sense in which this series is very much the integral of that sequence is that if you plop some rectangles down in here, again, think like Riemann sums, where the height of each rectangle is determined by the value of the sequence Sure, there's no area under each dot. Each dot has width 0, but there's also nothing going on between any two dots because the domain is just the integers. So the height of this first dot is A1, or I'll just label this as A1, this is A2, this is A3, this is A4, and so on. Then the area of each of those rectangles is very easy to calculate because they all have width 1. Right, the width of each rectangle is 1 because the domain here is just the natural numbers, so 0, 1, 2, 3, 4, 5. which means that the area of the first guy, the area of this first rectangle is A1, the height, times its width, which is 1. The area of the second guy is just A2. The area of the third guy is just A3. The area of the fourth guy is just A4, and so on. So in a very real way, the series sigma n from wherever, I guess I wrote it as a 1, starting at 1 here, 1 to infinity. An is, it's literally the area of all the rectangles which you could think of kind of as the area under the sequence, right? I'm going to come back to this picture at the start of class on Wednesday to prove, or at least convince you of the truth of our first important theorem regarding infinite series called the test for divergence. And that will be one of many tests called convergence tests that we'll put together for for series, for infinite series. So next time we're going to prove a couple theorems. That'll be one of them. The other one I'm going to prove is a theorem on geometric series. And we will talk about these things called telescoping series, all of which are a series that we'll be able to kind of work everything out about. They're the nicest series in a sense. After that, we're going to move into something called the integral test, where I will be relating the series to an improper integral, and we'll be able to tell whether one converges or diverges based on the behavior of the other. But that's all going down the road. So I'll go ahead and wrap it up here. Yeah, thank you for that reminder. You guys are good to go. And then Fergus, let me go ahead and make a breakout room so we can chat. So that's it. That's the end of class. I'll see you guys on Wednesday. Take a look at the homework. It's going to be opening up in the next few minutes. Okay, Fergus, if you want to join that, I'll follow you in and we can chat. All right. Yeah, so what happened? Were you able to find the work or find any files with the work in it? I saw the last email, but I saw an email a few days ago, but I don't think we ever got to a conclusive place.
Yeah, all of them is like I scanned it and then I submitted it to my phone, and I was scanning it with my I was sending it to the, how you call it, the note app, I think. Yeah. And then I don't know, I scanned everything, it only showed up, I only scanned 3.
So when you look at your phone, does it still have the scans with problems 12 and stuff?
No, doesn't. It only has the like the three ones I sent you.
Okay.
Like in one of them, you can see like under.
Yeah, I saw the problem number on the side of the page. Yeah, like you can't see the
number 12 is under number 13. So I don't know.
Do you have the papers lying around anywhere still? Is that something we could find? If you have those, I can grade it with that. That would work for me.
I'll have to look for them.
All right, then let's do that. Yeah, let's see if you can find those, because I mean, it is true that the final can replace a low midterm here. So if I couldn't give you credit for those problems, it's not the end of the world, but I really don't want that to happen. So let's see if you can find those papers. And if you can, then I can go ahead and give you the credit for those problems. But without the work, the most I can do is 2 points, because the way the rubric breaks down is that the answer itself is worth 2 points. And then the other 8 points on each free response problem come from like the steps on the work. So if you can find those papers, that would be awesome.
Hopefully.
Okay, yeah, I'm not doing anything right now. I can actually wait for a second. I'm just going to turn this off and pull up my email.
All right. I can't even find them. I don't even know.
Just 1 second, Fabrice. I'm sorry. What's up, baby? Yeah, give me just a minute. Yeah, I will. I just haven't had a chance to look yet. All right. So no luck finding them so far?
No. But I have a bunch of like papers, and I know I threw some away yesterday because I had too much papers up here. But I can't even find them.
That's all right. So take your time and see if you can hunt those down. If you can, that would be really nice. And if not, then I'll have to, I guess I'll have to ask my chair what we can do, because it's kind of a difficult situation, because it's very hard for me to assign a grade without the work. So see if you can find those. That would definitely be best. And I think 15 minutes before I got to go anywhere. So I can hang out here if you want to look, or if you want to get back to me later, either one is okay.
Well, yeah, I'll look at, because I also have another class I have to go to right now.
I got you. Okay, yeah, just send me a Canvas message and let me know. If you find them, that's awesome. If you don't find them, tell me that, and then we'll try to figure out what we can do from there, okay?
All right, thank you.
All right, man, take care. Oh, Elijah, Hannah, is there something you guys wanted to ask about? All right, I'm gonna go ahead and end the meeting.